Welcome to The Explainer. Today, we're diving into something absolutely crucial, setting off on a journey into the world of pure, absolute analytical precision. We're going to unpack a brilliant mathematical and chemical technique used in chromatography to achieve flawless accuracy. Let's get started.
So, picture this. How on earth do you measure trace elements when even the tiniest little instrument fluctuation completely ruins your data? Seriously, think about that for a second. When you're performing trace or ultra-trace analysis, we're talking about parts per billion environmental testing or super rigorous pharmaceutical quality control, the stakes are microscopic. A tiny variation in how much liquid an instrument injects, or just a momentary drop in instrument stability, can totally throw off your results. It'll literally ruin your entire day in the lab.
To figure this out, here's our game plan. First, we'll look at the trace analysis problem, then the internal standard solution, followed by calculating response factors. After that, we'll analyze an unknown sample, and finally, wrap up with how to choose the perfect standard.
All right, kicking things off with Section 1, the trace analysis problem.
Normally, you might just reach for the external standard method. But here is the villain of our story. It heavily relies on knowing the exact, precise volume of the injected sample. It completely depends on the mechanical perfection of your injector loop or your syringe. And honestly, if that syringe is off by even a microscopic fraction between your standard run and your sample run, your quantification is totally compromised. That's exactly where the internal standard method swoops in to save the day. It completely bypasses that vulnerability by compensating for those physical imprecisions using brilliant relative response ratios.
Moving right along to Section 2, the internal standard solution.
Okay, so what exactly is this method? Basically, an internal standard is a reference compound that you add at a known, specific concentration right into every single one of your samples. I like to think of it as dropping a steadfast anchor straight into the chaotic sea of your sample mixture. Because this anchor goes through the exact same instrument fluctuations and injection volume changes as your target compounds, well, whatever happens to the sample happens to the standard.
Take a look at this illustration. Over on the left, you've got the chromatogram of the standards, and on the right, the actual sample solution. Notice how in both cases, the internal standard, represented by that specific elution peak, is right there. Instead of relying on absolute peak areas, which bounce around with injection volume, we're simply comparing the areas of the compounds we want to quantify against the area of our trusty reference compound. So it really doesn't matter if you accidentally injected a tiny bit more or a tiny bit less volume. The ratio between your target peak and the internal standard peak stays perfectly, mathematically constant.
Which brings us to Section 3, calculating response factors.
Now don't let the math scare you. We're going to break this down piece by piece. Let's start with the foundation, equation 10.7. It says the quantity of the compound injected, little m, equals K, the absolute response factor, multiplied by A, the area of the eluting peak. If we were stuck using the external method, we'd hit a wall right here. Why? Because that absolute response factor K isn't just some built-in property of the compound. It depends heavily on how the chromatograph is tuned. Plus, M depends on knowing the exact injected volume. Not ideal, right? But watch this incredibly elegant workaround. We take the equation for our target compound, let's just call it compound 1, and we divide it by the exact same equation for our internal standard. Boom, we get a ratio. The mass of compound 1 over the mass of the internal standard equals K1 times area 1 divided by the K of the internal standard times its area. By just dividing them like this, we mathematically neutralize all those chaotic volume and instrument fluctuations. It's absolutely brilliant.
And here's the final piece of the puzzle for a standard run. Because the injected quantities, the masses, are strictly proportional to the concentrations in the solution, the injected volume cancels out entirely. This gives us the relative response factor. To find it, you simply multiply the known concentration of your target compound by the peak area of the internal standard, and then divide the whole thing by the concentration of the internal standard times the peak area of your target. Just like that, we've locked in a highly powerful, stable constant. All right, on to Section 4, analyzing the unknown sample. So how do we actually execute this in the lab? It's a really clean 3-step workflow. First, you run a solution containing known concentrations of your targets and your internal standard to calculate those relative response factors we just figured out. Step 2, and this is the absolutely crucial physical step, you take your totally unknown sample and you add a known quantity of your internal standard straight into it. Finally, step 3, you run that spiked sample through the column to get a brand new chromatograph. That gives you the new peak areas you need to plug into our ratios, which leads perfectly to the ultimate calculation, equation 10.9.
To find the unknown concentration of literally any component in our sample, we take the known concentration of the internal standard we just added, multiply it by that relative response factor from step 1, and then multiply that by the ratio of the new peak areas. No messy volume estimations, no stressing about slight instrument drift. It's just pure, precise chemistry translated into pure, precise math.
Finally, Section 5, choosing the perfect standard.
Now, this method is basically magic, but it only works if you pick the right standard. Our source outlines 5 strict non-negotiables here. Number 1, it must be pure and absolutely not present in the original sample. 2, its elution peak has to be completely well resolved from the other components. It cannot be hiding behind unknown peaks. 3, its retention time needs to be pretty close to the compounds you're trying to quantify. 4, you've got to add it at a concentration close to or slightly above your targets to ensure a linear response. And number 5, it has to be totally inert with respect to the sample components. The last thing you want is for it to react with what you're actually trying to measure.
So the next time you're reading a headline about some parts per billion environmental testing or a massive breakthrough in pharmaceutical purity, I want you to ask yourself, what was their internal standard? Because behind almost every single incredible claim of microscopic precision, there is a carefully chosen chemical anchor making that exact math possible. Thanks for joining me on this explainer, and I'll catch you next time.